Now suppose we have already discussed that magnetic material composed of a number of atoms. A magnetic material composed of number of atoms. Each atom have several orbits, and each orbit have a number of electrons, and due to the orbital motion of the electron associated with the dipole moment, and it is given by m is equal to n into mu b. We have already discussed these things. So this is the magnetic moment of each electron, and if we sum up this magnetic moment, we get total moment of the atom of the magnetic material. It may be 0 or it may be not equal to 0. So here discuss about those material for which this magnetic moment not equal to 0. That means total magnetic moment of the atom is not equal to 0. Okay, so that atom now behave like a magnetic dipole, because it has a resultant magnetic dipole moment. Each atom has resultant dipole magnetic moment, so each atom can be represented as a magnetic dipole, and its dipole moment is m0. Suppose this is an atom, it has a magnetic dipole moment m0 for each atom. That means this side is behave like a S, and this side is behave like a N, and this is called atomic magnet. Okay, magnet of atomic size. Why? This magnetic moment arises due to the orbital motion of the electron. Okay, now suppose this is a sample, okay, this is a sample, and this sample has several atoms, and the atomic magnet means atoms which are now considered as atomic magnet are randomly distributed over this substance or over this sample, like this. Okay, this is our atomic magnet. The atomic magnet are randomly distributed over the sample. Inside the sample, the atomic magnet randomly distributed. Their magnetic moment have random orientation. Okay, their magnetic moment has random orientation like this. Okay, as a whole, its magnetic moment, total magnetic moment, that is sum of the individual atomic magnetic moment, is equal to 0. That means this sample now does not have any magnetic property, because resultant magnetic moment of the sample is equal to 0. Now if you apply an external magnetic field of strength or intensity H, okay, if we applied an external magnetic field of intensity H, then what would happen with the sample? If we apply a external magnetic field, on the sample, then what would happen? Each individual atomic magnetic dipole, due to this magnetic field, align themselves parallel to the magnetic field. This is the property. Each atomic magnet, due to this external magnetic field, align themselves parallel to the magnetic field, because each atomic magnet feels an external torque, and due to this torque, this atomic magnet align themselves parallel to the external field. If we increase the external field, the number of atoms aligned parallel to the magnetic field increases. That means if we increases magnetic field, more and more number of atomic magnet align parallel to the magnetic field, and one time reach when all the atomic magnet align themselves parallel to the magnetic field. At that time, no more atomic magnet remain within the sample to align themselves parallel to the field. All the atomic magnet align themselves parallel to the field. We can say at that time the magnetic material become saturated and the sample become fully magnetized. So when the sample become fully magnetized, then how does this this atomic magnet alignment look like? Okay, this is your original magnetic field, external magnetic field. Okay, this is your external magnetic field. Due to this external magnetic field, all the atomic magnet align themselves parallel to the field. All the atomic magnet align themselves parallel to the field. All the atomic magnet align themselves parallel to the field. Okay, now all the atomic magnet align themselves parallel to the field, and you know that already we have discussed, since this is the alignment of the atomic magnet, this side is S, this side is S, this side is N, this side is S, this side is N, this side is S, this side is N, this side is S, this side is N. So this thing happen, we can consider when all the atomic magnet align themselves parallel to the field, then this thing happen. And you if you observe minutely, then you see this NRS cancel each other, 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 this NRS cancel each other. So NRS cancel each other in pairs. Okay, NRS cancel each other in pairs. Only one side of the material have S pole and other side have N pole. This S pole is not neutralized, so these S poles are not neutralized because there are no N poles to neutralize this S pole. Similarly, same thing happen here. For this N poles, there are no S poles to neutralize this N pole. So resultant, we have a resultant S pole this side and N pole this side. That means total sample now becomes one side. For the total sample, what happened? One side S pole is induced and other side N pole is induced. This is the direction of the applied electric field, and we say since this pole is S, this side is induced by S pole and this side is induced by N pole, so a resultant magnetic moment induced inside the sample. Resultant magnetic moment induced inside the sample. So magnetic moment is induced in the sample, or you can say the sample become magnetized. The S pole opposite to the applied field is generated, and N pole in the direction of the applied field is generated. So this sample now become magnetized. Okay, and magnetic moment of the sample now becomes M, because S pole or N pole, S cell is induced over this side, N pole is induced at this side. Okay, there is a separation, so total sample now becomes magnetized. So M is the total magnetic moment of the sample. Each sample have its own volume, so magnetic moment induced per unit volume is called I. I is called intensity of magnetization. Intensity of magnetization. Okay, intensity of magnetization. And you see more why does this intensity, why does this I arise? Due to this M. And why this M induced in the sample? Due to the external field. So more you applied electromagnetic field, more dipole align themselves, more is the magnetic moment, more is the I. So if you increase H slowly, your magnetic moment also increases, and as a whole your I also increases. That means I is actually depends on the external magnetic field. So I depends on the external magnetic field, and I is proportional to H. Okay, this increases of I with H valid up to the saturation level. When the magnetic material becomes saturated, that means all the atomic magnet align themselves parallel to the external field, that then no more magnetic moment induced, then M becomes its maximum value, so I becomes saturated, I becomes its maximum value. So up to that value I is proportional to H, I is proportional to H, and I is equal to chi into H. What is chi? Chi is a constant, that is intensity per unit magnetic field. So intensity developed within the material with the applied field is called susceptibility. So if a material for which H is low, so if a material for which we need very low amount of H, if a material for which if we required very low amount of H, so that very high amount of I is induced, for that sample chi is very high, and if very high H is required to develop a certain amount of I, we can say the chi is the minimum value. That means chi high means that that sample is easily magnetized, because for chi high value low amount of H is required to get high amount of I, that means high amount of magnetic moment, that means highly magnetized. So low amount of H corresponds to high amount of chi, because low H corresponds to high chi, that means high value chi, which actually signifies that we need very low amount of H to produce certain amount of I or a significant amount of I, or you can say that sample is easily magnetized because we need very H low value, and for which we need very high amount of H, then it corresponds to chi low value, that means that sample is not easily magnetized. Okay, chi is equal to I by H, it is called susceptibility of the sample of the magnetic material, that means sample of the magnetic material. And we always prefer high value of chi to convert a magnetic material into magnet, because for that material, since chi is high, we need very low H to have very high value of chi, very high value of I, that means that material is easily magnetized. High value of I means high value of M, high value of M means induction, that means this side is very high. Okay, so these things you have to understand the susceptibility. Okay, here we learned about the susceptibility, the definition, and one more thing, chi is a dimensionless constant. Okay, it has only values, no dimension. Okay.